In this video, we talk about why GPUs made the AI explosion possible. So we talked about GPUs in the last video where we actually consider the matrix trick that powers neural networks. And we discovered that that simple trick is the idea of matrix multiplication, which of course a regular math student would take for granted. But we saw how powerful matrix multiplications can be like that. And we saw that having to multiply matrices that have thousands of parameters has been made possible with GPUs, which is short form for graphics processing unit. As opposed to CPUs that work sequentially, GPUs can do parallel computation, and they are very good for, image rendering, complex computations, and all of that. So why GPUs made the AI explosion possible? It's simply because they can do parallel computations instead of sequential computations. So our learning objectives, by the end of this lesson, you'll be able to explain why CPUs became a bottleneck for modern AI. I mean, they were too slow because they have to do things sequentially, and understand how GPUs now perform massively at parallel computations. Describe matrix operations and tensor computations. I mean, we already did a bit of that in the last video. Understand why deep learning relies heavily on linear algebra and explain why GPUs enabled large language models, LLMs. So implement matrix and tensor operations in Python. So we go ahead to talk about the AI explosion, what really changed, what made it possible. So modern AI systems contain billions or even trillions of parameters. So that can be a problem on its own. So training these models requires huge data sets, massive mathematical computations, large amounts of memory, weeks or months of continuous processing. All right. So without GPUs now, training today's large AI models would be impractical because using CPUs that sequential will be very slow. So the AI revolution occurred because hardware became powerful enough to perform enormous amounts of computation in parallel. So let's quickly look at CPUs versus GPUs. So CPU, that central processing unit that we learnt about in computing, like I mean, I learnt about this in the say early late 90s and early 2000s in high school, right? So CPU has few, so it's more CPU is more like few powerful workers working. So a CPU is designed for running operating systems, managing applications, sequential processing. So the key here is the idea of sequential processing. And then of course it also makes complex decisions, but then it's sequential, and that's a big deal. So the typical characteristics of CPUs. So the features that it has cores. So you have 4 to 64 for CPU, then it is optimized for sequential tasks. And the strength is that it is flexible. The weakness is that it has limited parallelism. So it cannot it's more like it cannot do things, it cannot do different things at the same time. It starts to do things one after the other. So a CPU can be imagined as a small group of highly skilled engineers solving problems one after another. So it's more like I solve a problem, the next person solves it, the next person solves it, as opposed to GPU where every engineer is solving one part of the problem at the same time. So talking about GPU, so, we saw CPU as few powerful workers, right? But GPU can be seen as thousands of workers. So, a GPU is designed for graphics rendering, matrix calculation, scientific computing, and deep learning. And the typical characteristics include the cores now. You have thousands of cores as opposed to 4 to 64 cores for CPU, and they are optimized for parallel computation as opposed to sequential computation that we have in CPUs. Then the strength is they have high throughput, while on the other hand, of course, those CPU is just flexible, right? The weakness is that it is less flexible. It has less flexible control logic. So in essence, a GPU can be imagined as thousands of workers performing similar calculations simultaneously. Nobody needs to finish a task before the other person takes it up. So that makes the whole time faster. So it means that if you the same job that um five engineers will do in CPU in 5 hours, five engineers will do that in 1 hour, because they are working they divide the work into five and do each part at the same time. So that's a very rough idea of explaining the idea of CPUs and GPUs. Now, why AI loves GPUs, right? Most neural network computation involves the equation y equals wx plus b, so which we explained in the last video. In fact, the practice problem I solved there, in case you have not seen that video, that the ninth video that is, so you want to go back and see the second practice problem. So I took time to explain each parameter in some depth. So why AI loves GPUs, right? Most neural network computations involve the equation y equals wx plus b, where w is a weight matrix. So the weight matrix determines how important each parameter is in the input vector. So X is the input vector and B is a bias vector. So this computation must be repeated billions or trillions of times during training. So because many of the multiplications are independent, they can be executed simultaneously on a GPU, right? So it's more like you want to compute. We already know the idea of the computation of matrix, right? So you can compute each element of a matrix. It already has a formula. So using GPUs now, you can have GPUs working on computing instead of waiting to compute the first row, first column, second row, second column, and things like that. You have GPUs working on all these components simultaneously. That's why you get very fast answers when you're working with AI. Now we go to matrix multiplications and we start with, of course, we did this in the last video, I think. So a matrix is simply a rectangular arrangement of numbers. So A, you have 1, 2, 3, 4, B, 5, 6, 7, 8. And we can have matrix addition. So two to add two matrices, just add corresponding elements. So 1 plus 5 is 6, 2 plus 6 is 8, 3 plus 7 is 10, and 4 plus 8 is 12. A plus B is then 6, 8, 10, 12. So notice that every addition can occur independently. So, since we're adding components, imagine instead of having one engineer or four engineers do so one does 1 plus 5, 6. Then the next one go after doing that, the next one now says 2 plus 6, 8. So instead of waiting to do that one after the other, all the four engineers can just do their part and supply the answer, and everything is done in a very short time. So notice that every addition can occur independently. So this makes matrix addition highly parallelizable. So we can compute the four results at the same time, thereby saving maybe reducing the time by one quarter if you like. So matrix multiplication then is which this is the most important operation in AI. So the most important operation in AI is matrix multiplication. So where you have A is 1, 2, 3, 4, and B is 5, 6, 7, 8. So you want to compute A multiplied by B, right? So the first element will have to be 1 times 5 plus 2 times 7. All right. So 1 times 5 plus 2 times 7. Yeah. So you have 5 plus 14, which is 19. The second element now will have to be 1, 3 times 5 plus 4 times 7, I believe. So the second element is, okay, 1 times 6 multiplied by 2 times 8. So that is 6 plus 16, which is 22. And the third element is 1 times 6 multiplied by 2 times 8. So that is, okay, the third element is 3, 5, 4, 7. 3 times 5, 4 times 7, that's 43. Well, I mean, for me, I really don't like this. I have a very simple way of showing it, very straightforward. If you can get that, you're very fine. You'll be fine. So imagine now you have A to be 1, 2, 3, 4, and B is 5, 6, 5, 6, 7, 8, and you need AB, right? All you just need is you have 1, 2, 3, 4, and you have 5, 6, 7, 8. So what you do, you look at the first matrix. For the first matrix, you check. So of course we need AB, right? So you check how many rows does the first matrix have. That's two rows. So because that's two rows, then you write each of these columns 5, 7, 6, 8 twice each. So you have 5, 7, 5, 7 on one hand, 6, 8, 6, 8 on the other hand. Then apart from that, now you then write do not have 1, 2. So 1, 2 is in the first row here. So you write 1, 2 here, 1, 2 here. And then secondly, you have 3, 4. So 3, 4 is in the second row. So you have 3, 4 here and 3, 4 here. And so once that is done, you can then have AB to be 5 times 1, 5, 7 times 2, 14. Then 6 times 1, 6, 8 times 2, 16. Then 5 times 3, 15. 7 times 4, 28. 6 times 3 is 18. 8 times 4 is 32. So AB then is equal to 5 plus 4, that's 19. 6 plus 12 is 22. 15 plus 28 is 43. 18 plus 32 is 50. So for me, I think this is a more straightforward way of going about this. So if you can master this, it's easier to do so because I mean it can get really confusing, the way it's explained here, but you can choose. And the interesting part is you can also write a Python code to get that done. So here you just import NP as a numpy because you are going to use an array function. You're going to declare each metric as an array. So A now is NP array. Then you each row is declared as a list. So you have one, two, three, four. Then don't forget the square brackets and the brackets outside there. So same thing for 5, 6, 7, 8. And then to multiply A and B, you can then have C is A multiplied by B. So print C now, and you get 1922 4320, like we got like what we have here already. So you get 1922 43 50, just exactly like what we have right here. Okay, so next is why GPUs excel at matrix multiplication. So notice that each output cell in the result matrix can be computed independently. So we already know so from what we have here, all you just need to know is what you need to put together to get each of these items. So, and it can be done independently. You don't need you don't need this to get this. No, each of them can occur independently. So for example, core one computes, so you can have a core that computes C11, a core that computes C12. So by the way, all this C11, C12 is just one way to number it. So this is row one, column one, row one, column two. So row two, column one, row two, column two. That's why you see this one is C11, C12. So this is now so this is C11, C12, C21, C21, and then C22. That's basically how we number that. So each one can be computed by different cores. So core 1 computes C11, core 2 computes C12, core 3 computes C21, and core 4 computes C22. So large neural networks may involve billions of such computations. So GPUs execute many of them simultaneously. So that saves a lot of time. So let's talk about deep learning, which is mostly matrix multiplication. So consider a neural network layer where the input vector is 1, 2, 3, and the weight matrix is 0.5, 0.2, 0.1, and 0.7, 0.5, 0.32. The layer output is then y equals wx. So for example, you have the first neuron, that's 0.5. Yeah. So the first neuron now will be 0.5 multiplied by 1. So 0.5 multiplied by 1, 0.2 multiplied by 2, 0.1 multiplied by 3. So you have 0.4 plus 0.5 plus 0.4 plus 0.3, which is 1.2. Then the second neuron is 0.7 multiplied by 1, 0.4 multiplied by 2, 0.3 multiplied by 3. So that's 0.7 plus 0.8 plus 0.9. All of that goes to 2.4. So the output then is 1.2, then 2.4. So then if you multiply all this, we have 1.2, 2.4, just declare the array and all of that. So that's deep learning. That's the brain box, the fundamental thing that deep learning is about. It's mostly matrix multiplication as seen right there. Now let's talk about from matrices to tensors, right? So, we have scalars, we can then go to vectors and then matrices, and then we now go to tensors. So matrices are only two-dimensional structures, as we have seen, rows and columns. Modern AI requires higher dimensional data structures called tensors. So you can have a scalar number that's zero-dimensional. Say a number like 5 is zero-dimensional. That is just a scalar. Then from scalar, you can move on to vectors where you have a row vector, a column vector, like we've been saying before. So this is one dimensional. On the other hand, you can have a matrix, which we also have like 1, 2, 3, 4, which is two-dimensional. But tensors can be three-dimensional, four-dimensional upwards. So example of tensors can be things like color images, video data, transformer activations, and model parameters. So a very good example would be this. You have an image tensor. A color image often has dimensions like height, width, and channels. For example, you have 224 for height, 224 for width, and three channels, where the channels correspond to red, green, and blue, like that. So if that is the case, of course, we can represent using numpy, right? So import numpy as np. So image can now be np.random dot ran 224 by 3. Then the image shape then comes out as 224 like you have here. So of course we can even print the image itself. Let me just do something about the image. Print, if I say print image, let's see what happens. Okay, that's not what I want to do. Print image. Yeah, so you see see the number that the image represents. So they have these tons of, so it's a 224 by 224 by 3 kind of uh stuff like that. So it's such a big deal. Yeah. So that's because machines, or if you like, computers, do not understand words and images. So they understand pixel for images and they understand embeddings for words, like we've been explaining in previous videos. So imagine this now. Why tensor computations need GPUs? So consider a high resolution image like 1024 by 1024 by 3. So the number of values would now be 1024 by 1024 by 3, which is 3,145,728. So here you have over 3 million numbers must be processed. So deep neural networks repeatedly perform computations on tensors of this scale. So GPUs make this possible by distributing the workload across thousands of processing cores. So thereby getting the work done faster. Like we saw, I think in the last video, we saw a case of, something such one, maybe a billion operations of school. So happening within less than 0.2 seconds, something like that. So then we also have the idea of batch processing. So neural networks rarely process one sample at a time, right? So instead, they process batches. So suppose you have batch size 128 and the input dimension is 768. So input tensor shape is 128 by 768. And then weight matrix shape is 768 by 3072. And then the output shape becomes like 128 by 3072. So this requires millions of multiplications for a single layer. Okay. So batch size 128, input dimension 768. So input tensor shape is now 128 by 768. So if we now do the weight matrix shape now, you have something like 768 by 3072. Altogether, you have output shape will now be like 128 by 3072 because now you have 128 by 678 multiplied by 678, 768 rather, by 307. So this crosses out, so you can have a 128 by 3072 output matrix. So this requires millions of multiplications for just one layer. So, and that's why batch processing is important. Imagine this now, number of operations, yeah, an example of number of operations. So you have matrix multiplication 128 by 768, then by 768 by 3072. So approximate number of multiply add operations will be 128 by 768 by 3072, which is 301,989,888. So nearly 302 million operations just for one layer. So modern large language models contain hundreds of such layers. Okay, so the GPU architecture for AI is now so modern AI GPUs contain streaming multiprocessors, that's SMs. So these are groups of execution units that manage many threads. Then you have the CUDA cores, which perform arithmetic operations. Then you have the tensor cores, which are specialized hardware for matrix multiplication. So tensor cores accelerates operations of the form A multiplied by B plus C, which WX plus B looks like on the general, right? That um, the Z, right, equals WX plus B. And this appears constantly in deep learning workloads. So then we talk about tensor computations in deep learning. Suppose input tensor is X and the shape is 32 by 52, while the weight matrix is W and the shape is 512 by 2048. Of course, you can see 32 by 512, 512 by 2048. So at the end of the day, 512 crosses out. So we have 32 by 2048 for Y equals XW. So you have 32 by 2048 going by the rule of multiplication. But then the number of operations will have to be 32 by 512 by 2048, which is 33,554,432 thousand. 3,554,432. So more than 33 million multiply add operations are required, and this is only one layer. So a transformer model may contain hundreds of layers like that. So the question is why LLM training is expensive? Why are LLM training is expensive? Of course, that's one debate that has been raging about the whole idea of AI. They need to build data centers to store massive data, that powers the whole uh, large language model things and all that. So large language models contain enormous number of parameters. So imagine for a small transformer, the approximate parameters are in millions. For GPT-2, I mean, that was the beginning of ChatGPT and everything. So for GPT-2, you have like 1.5 billion approximate parameters. For GPT-3, you have 175 billion approximate parameters. So And for modern frontier models, we have hundreds of billions or more. So training requires forward pass, loss computation, back propagation, which has something to do with chain rule in mathematics. And you have weight updates, because you have to do some optimization in the process. So these steps are repeated over trillions of tokens. And we know tokens are small bits of words. If you prompt AI, so whatever your prompt is going to be broken down into same maybe into word chunks, and then they are assigned vector numbers and everything. So those are tokens. So these steps are then repeated over trillions of such tokens. So then we have matrix operations inside transformers. So each transformer layer performs multiple matrix operations. So you have a query matrix Q, and you have XWQ, and you have the key matrix that K now, that's XW sub K for the key now. And you have the value matrix, which is V equals XW sub V. So these three large matrix multiplications are performed immediately, So your query quickly done, key matrix, so something, a key associated with that, and then you get the value. So, and then that also leads to the concept of attention computation, which is one of the revolutions which brought about the whole idea of transformers in artificial intelligence. And one paper that really popularized that is Vaswani et al. 2017. That was not peer reviewed, but it was just put, well, I don't know, technically, it was put on archive, and it has more than 200,000 citations right now because it brought the whole idea of attention and transformers like that. So attention computation. Attention scores are computed using QK transpose. This operation measures relationships between tokens. So for long sequences, this becomes extremely expensive. And then graphics processing units are essential because attention calculations involve huge matrix operations. So, and then we have the feed-forward network. So after attention, another set of matrix multiplications is performed. So you have typical operation H equals XW sub 1, followed by Y, which is HW sub 2. Again, GPUs accelerate these computations dramatically, right? So, mm, you then have, of course, we can do this kind of thing now. Imagine you import NumPy as NP, and you have tokens. Tokens, you generate random tokens, a 4 by 8 kind of matrix, and you have your WQ, that's for query, I believe, and then WQ for the key. So 8 by 8, 8 by 8 each, and this can work, right? So this 4 by 8 by 8 by 8, you're going to get another 4 by 8, and that's exactly what we have here. So 4 rows. Okay, so Q now is tokens multiplied by WQ. So 4 by 8, 8 by 8. So, and then K is also this now. So at the end of the day, your attention cost is going to be a multiplication of Q multiplied by K dot T. Um, yeah. So attention cost is now Q multiplied by K. Okay, the transpose of K now. Let's see. Um, okay, K is tokens multiplied by WK. So you multiply this Q now by this key, and you get that's at the end of the day, you get a 4, 1, 2, 3, 4. You get a 4 by 4 matrix. And how that is working is this now. Uh token Q is tokens 4 by 8 multiplied by WQ. That's going so 4 by 8 by 8, that's 4 by 8 again. And then this K is also 4 by 8. So it's more like you have 4 by 8 multiplied by 8 by 4. That's why you end up getting a 4 by 4 matrix like this. So that's how it all comes out. So these are your attention scores now. So this scores now, the bigger the value is, tells you the weight of each token and which one you should really pay attention to, like that. All right. So I think I talked about that a little bit in the very first video, talking about the five equations that power AI. Now, why GPUs triggered the AI revolution, right? Before GPUs, training was extremely slow because we're using CPUs. Neural networks remained relatively small, and research progress was limited. But after GPUs, right, matrix multiplication became dramatically faster. Larger data set became practical. Deeper neural networks became trainable. Transformers became feasible, and large language models became possible, like that. So the AI revolution emerged from the combination of massive data sets. So we can have massive data sets and of course better algorithms and GPU accelerated parallel computation. So if you combine massive data sets, better algorithms and GPU accelerated parallel computation, then you have the AI boom right there. In summary, we've seen so far in this video that the AI explosion occurred because neural networks are fundamentally large collections of matrix and tensor operations. And the key ideas are that CPUs excel at sequential processing, while GPUs excel at parallel processing, and that so they can power the whole AI revolution. Then deep learning is dominated by matrix multiplication. So deep learning is more of matrix multiplication done billions of times or so. Then tensors generalize matrices to higher dimensions. GPUs process tensor operations efficiently, and transformers rely heavily on matrix multiplication. So modern LLMs require enormous computational resources. So the single most important reason GPUs enabled modern AI is that they can perform billions of matrix and tensor computations simultaneously, making large-scale neural network training practical. So then we have our practice questions. As usual, I get to solve two of them. So let's see. I think these ones you can see 1 to 10 straight here. And I'm going to solve problems 10 and 14. Solving problems 10 and 14. So problems 10 and 14. So problem 10 says compute the number of multiply add operations required for 64 by 512 and 512 by 2048. That will simply be 64 multiplied by 512 multiplied by 2048 right there. So, but we'll get there. Then I'll be solving 14 too. So I think you can see 11 to 20 here. But I think if I shrink it a little bit, you get that. Okay, I can't. So let's just make it bigger so we can just show them in batches. So here you can see 11 to 18 very clearly. So I'll be solving 14. 14 says during self-attention, a model computes QK transpose if Q and K both have shape 128 by 64. What is the shape of the resulting attention score? Okay, we are going to see that also. Then, of course, to see the rest, you can now see 13 to 20. So let's go straight and deal with these issues, problems 10 and 14. So let's start with problem 10. So for problem 10 now, we have this. We want to compute the number of multiply add operations, multiply add operations for for 64 by 512 and then 512 by 2048. You can see they are all powers of 2. So and we know that for matrix multiplication, for matrix multiplication, the total number of multiply add operation is m by n times p. And in this case, we have m to be from the problem, we have m is 64, n is 512, then p is 2048. So we have m 64, n is 512, p is 2048. So we have we have 64 by 512 times 2048. 2048, and all of that ends up being 67,108,864. 864. Yeah, we can confirm that, right? So 64, 512, 2048. 64, 64 times 512 times 2048. That is 67,108,864. like that. So that's what we get. Then that takes care of problem 10. So we move on to problem 14. Okay, well, I can just conclude now. So 67,108,864 multiply add operations, multiply add operations are required. Okay. And then we have problem 14. Problem 14 now. So we want to determine the shape of the attention score matrix. Attention score matrix Q K transpose, right? So let's go. So the solution is this now. I thought I had changed that. So the solution, so given Q and K both have uh, both have shape 128 by 64, right? So attention scores, attention scores are computed as QK transpose. So we can go then and say in step one, we can find the shape, find the shape of K transpose. Of course, transposing swaps rows and columns. So since K has shape 128 by 64, so that implies that K transpose will have shape 64 by 128. So that's what we have there. Then on the next one, we then have this now that we now have step two, right? Step two. So we can multiply the matrices, matrices. So to multiply matrices now, multiply matrices. So we have we have QK transpose, QK transpose. That means Q, which is 128 by 64, multiplied by 64 by 128, which K transpose represent, like we know here. So, but then this is the usual thing we will do. So you see this 64 by the 64 inside. So we can carve that out. And then what we have left is 128 by 128. So that the inner dimensions. So this is simply 128 by 128 in short. That's what QK transpose gives us. So we see that the inner dimensions match. So they have to match for us to be able to multiply. If they don't match, it can't work. The inner dimensions match. So these have got to match for this to work. If they don't match, then we can't have multiplication, that multiplication. So the inner dimensions match. So multiplication is valid. Multiplication is valid. That's why I said about for two matrices to be multipliable, it means that the number of columns in the first one must be equal to the number of rows in the second. So multiplication is valid. So the result takes it takes rows rows from the first matrix, rows from the first matrix, Once it is confirmed that the inner dimensions are okay, are the same, so we then take rows from the first matrix, which is 128 here, this 128, and then it takes columns from the second matrix, columns from the second matrix, which is also 128, and that's this one, this here. So we can then say, therefore, the output, the output shape, the output shape is 128 by 128. So the interpretation then, the interpretation is that each each of the 128 tokens, each of the 128 tokens is compared with every other token. It's compared with every other token. And then we have that the number of attention scores. You see, that's a lot. Number of attention scores now. Number of attention scores will now be 128 times 128. 128 times 120, that should be 16,384. So we have these attention scores to compare. So overall, right? Overall, the attention score, the attention score matrix matrix shape, matrix shape is 128 by 128. So just for confirmation, let's check 128 by 128. What does that give us? 128 by 128. So that's 128 times 128. So that's 16384, which is correct. 16384. Yeah, so on that note, we are done with this particular video on why GPUs made the AI explosion possible. So these are the first 10 problems which you want to try your hands on. And okay, you can have like 11 to 18 here, and then we can 11 to 18 first of all, and then the rest. Let me know how helpful this is for you. If there's something else you'd like me to try out, feel very free to let me know. So um if you have subscribed to this channel already, I thank you very much for doing that. And if you have not subscribed, just tell me what exactly is holding you back. So why not just go ahead right now, hit the notification bell so that and then hit the notification bell so you can always get alerted each time a new video is released. Having done that, you can also become a member of this channel by clicking on join. That gives you special privileges, that you'll find out as you click. Ultimately, don't forget to comment, like, and share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.